Hello and welcome to Diplomatic Derivatives. In today's video, we are going to continue with our group theory basics. So this video, we are going to continue with cyclic group theorems, and the theorem that we're going to touch today is about finding the generators of a cyclic group. So this we're going to do with the help of two parts in the theorem. The first part, which is about being the cyclic group being finite, and the second being cyclic group infinite, right? So let's see, first try to understand each part separately, and then we'll move forward towards the proof. So before jumping into the main theorem, we need to make sure that it's clear in our mind what is the theorem itself, what is it asking us to prove, because once that's clear, we will be able to understand each step. Right? Because there are going to be multiple steps, there are going to be so many different terms that will be coming forward, coming in front of you. So make sure you do not forget till the very end what are we actually trying to prove. So we are basically finding the generators of a cyclic group. We know we already did a video where we explained cyclic groups and the generators of a cyclic group. So make sure you check that out in the group theory playlist. All the videos are in the playlist. So make sure you understand that concept first. Also understand the concept of order of a group as well as finite and infinite groups. So these are the terms that we'll be witnessing in the future slides. Now, question to find the generators of the cyclic group. How are we doing that? We are doing that with the help of two parts. The first part is that the cyclic group is having a finite order. That is, we have a particular number of elements inside a group. We know the order of that group. Okay. Second is that it's of an infinite order. That is, we do not know the exact number of elements. It's infinite. It continues, right? So what are the generators in a finite cyclic group, and what are the generators in an infinite cyclic group, right? The theorem says that for a finite cyclic group, the generators are A and A raised to k. And for the infinite cyclic group, the generators are A and A raised to -1. A and A raised to k means it's basically generated by A raised to k. Okay, so instead of writing A separately, we do not write that. We just say the generator is A raised to k. Okay, I think that's a typo. So just the generator is A raised to k for a finite cyclic group. This is the first part of the theorem. The second part of the theorem says that for an infinite cyclic group, the generators are A and A raised to -1. All right. And for the part about the finite order, we will be using one of the topic from the number theory basics. So make sure you check that playlist as well, because in that playlist we have already explained what is GCD. That is the greatest common divisor. All right, because with the help of the greatest common divisor, we will be able to prove that for a finite cyclic group, the generator is A raised to k. All right, so let's see. First of all, we start with part A, which is the cyclic group is finite. If order of G is equal to n, that is, G is a finite cyclic group of order n, then A raised to k is a generator of G if and only if GCD is equal to 1. This shows that we are going to prove the theorem in both sides. So we're going to prove in this direction as well as the opposite direction. Okay. So let's suppose we take a group. Okay, and since it's a cyclic group, so it has one is the identity element. Other we have, let's suppose we have A, then we have A raised to 2, okay, then we have A raised to 3, and that's it. Okay, so this is a finite cyclic group. Why is it finite? Because we have a particular number of elements, so we know the order of the group, that is 1, 2, 3, and 4. 4 is the order of the group. Let's suppose that n is 4. Okay, that is, it's a finite cyclic group. So what is the generator of the group? A raised to k. All right. So we first go in this first direction, that is, we assume that GCD is equal to 1. What is k and n? First of all, k is the power of the element, which we are going to prove is the generator, right? So this is the k is the power. N is what? N is the order of the group. All right, and the greatest common divisor between k and n must be 1. All right, now take the first direction. Assume that GCD-Kn is equal to 1. We are going to assume that for the greatest common divisor of k and n, it is 1. So we prove that AK is a generator of the group. Now, the order of an element a raised to k in a cyclic group of order n is given by. This formula is what you need to remember. For finding the generator of a cyclic group, we take the order of the of that generator. We are going to take the element and we are going to say, let's suppose the order of that cyclic group of that generator is this. Okay, because this is the actual formula, right? So what is the formula? Order of a raised to k is equal to order of the group divided by GCD-Kn. Again, this we have already done in one of the videos in the number theory that includes a Euclidean algorithm. And one more topic was there, so make sure you check that out, because in there we have explained the formula as well. Now, order a raised to k is equal to order of a raised to k, that is order of the element which we are going to prove is the generator, is the group order of the group divided by GCD-Kn. Right now we have already taken that GCD-Kn is equal to 1. We assumed that, right? So in place of GCD-Kn we can write 1, right? So since GCD-Kn is equal to 1, we have order of a raised to k is equal to n divided by 1, which is equal to n. So what did we get? We got that order of a raised to k is equal to n. What is n? Order of the group. So order of a raised to k is equal to order of the group, right? What does this mean? That a subgroup which is generated by a raised to k means, let's suppose a raised to k generates something, right? That group is equal to the group G. Why? Because both of the things have the same order. This order is equal to this order, right? So whatever is generated by AK has a similar, or that group which is generated by AK has a similar order of the group G. Therefore, AK generates G. Alright, this is how we do the first direction. We assume GCD-Kn is equal to 1. We use the formula, that is order of a raised to k is equal to n by GCD-Kn. Since GCD-Kn is 1, order of a raised to k is equal to n by 1, which is equal to n. Both the orders are same, that is order of AK is equal to order of the group. Therefore, the subgroup which is generated by AK has order n, which means a raised to k generates G. Okay, now we go to the opposite direction. That is, now we are going to assume that AK is a generator of G, and we must know that we must show that this GCD-Kn is equal to 1. Now, since AK generates the entire group, this is what we are assuming, right? Since we are assuming that, what does this mean? That the order of AK must be equal to order of n, right? This is what we are assuming, that AK generates the group. So we know that AK order of AK will be equal to n. That is order of G, right? So what we are saying is order of AK is equal to n. Now what is the formula for order of AK, which we also used in the previous part? That is n divided by GCD-Kn. So in place of order of AK, we write n divided by GCD-Kn, which is equal to obviously n. Now this n and n gets cancelled. Therefore, GCD-Kn is equal to 1. So we used one formula and we proved both the directions. Alright. So remember, in part A, which is about the finite order of a cyclic group, we use the formula order of a raised to k is equal to n divided by GCD-Kn, and we proved both the directions. Alright. I hope that's clear. Now we're going to move to the second part B of the theorem. That is, G is of infinite order. Now how do we do that? If G is generated by A is an infinite cyclic group. Infinite means it is never ending, so it just keeps going, right? We do not know the order. So here we are not talking about the order at all. Then the only generators are A and A inverse. This is what we are going to prove. What are the generators? For infinite cyclic group, generators are A and A inverse. For a finite cyclic group, the generator was A raised to k. For an infinite cyclic group, the generators are A and A inverse. So we see how do we prove that. An infinite cyclic group, let's suppose we are taking Z plus. Now this for this particular group, we have already done one of the videos in the very beginning. So there we have explained the entire part about how Z plus is a group or not. So also you make sure you check that video. Now it's this Z is integers under addition. Now it's a infinite cyclic group. Okay, it keeps going, where the group elements are a raised to n such that n is element of Z, right? So n could be 1, 2, 3 and so on, minus 1, minus 2, minus 3, so on, because it's integers, right? So it can be plus and minus both. So a raised to n would be a raised to 1, a raised to 2, or a raised to minus 1, a raised to minus 2. That's anything. It could be anything. We are basically proving that the generators are a raised to 1 and a raised to minus 1. So we are just taking a group. Let's suppose we are taking Z plus. Suppose that B is equal to a raised to k. Now we are taking one element, okay, from the group. We're taking one element, let's suppose that is a raised to k, and we take it as B. So B is equal to a raised to k, any element from the group Z. For some non-zero integer k, we need to determine when B generates G. Okay, we're just taking an element, let's suppose a raised to k, and we are going to show that when does B, that is this element a raised to k, generates G. Alright, why are we taking a raised to k? Because it was, since let's suppose we assume that since in a finite group, finite cyclic group, a raised to k generates a group, right? We already proved that. Does a raised to k also generate for an infinite cyclic group? Does it or does it not, right? So we are just taking, let's suppose we take the same a raised to k and we are going to prove it for an infinite group. If it's true, okay, a raised to k generates. But if it's not true, obviously then there is a difference between a finite and infinite, right? So that's what we're going to do. First case, we are going to take, let's suppose k is equal to plus 1 or minus 1, right? So if k is equal to 1, then B is equal to A. Clearly the generator. How? Because k, when k is 1 and we are saying that, let's suppose B is equal to a raised to k, right? So a raised to k, you put k is equal to 1, you get a raised to 1, which is A. So this A is equal to B then. Alright, so that's one generator. If k is equal to minus 1, then in place of k you put minus 1, right? So what do you get? You get B is equal to a raised to minus 1, also a generator. How? Since a raised to minus 1 will give us a raised to 0, a raised to minus 1, a raised to minus 2 and so on, which is equal to G again, right? Which is Z. Because also you can see here a raised to 0 is equal to 1. 1 is the identity element part of the group, right? Also we'll get all the elements of Z. Both A and A inverse generate all powers. So in the first case, we saw that when we take k is equal to plus 1 or minus 1, we get all the elements, right? Next, let's suppose the order of k, let's suppose k is greater than 1. The value of k is greater than 1, right? So in that case, it could be 2, 3, 4 or anything, right? Or minus 2, minus 3, minus 4 or anything, right? Therefore, then what do we see? A raised to k generates E, AK, A2k, A3k and so on. So what did we see? K is greater than 1, right? It's not, sorry, I in the previous sentence I just said minus. That's not true. We are saying only k greater than 1, not less than 1, right? So when k is greater than 1, we get AK, A2k, 3k. We are not getting the negative powers. Here we do not get the negative. We only get the even powers, right? Therefore, this AK cannot produce all exponents because it only reaches multiples of k. For example, A2 generates only even powers. It cannot reach A1. If we are having a raised to 2 as a generator, let's suppose, right? So it will give us a raised to 2, a raised to 4, a raised to 6. Where is a raised to 1 or 3 or 5? We do not have odd powers. We will have only even powers, right? So it will only generate a group which is of even powers. That is, it's creating a subgroup, but it is not giving us a group, right? Therefore, we cannot have k greater than 1, right? Hence, this is a proper infinite subgroup. It's a subgroup, not the whole group. All right. Therefore, in an infinite cyclic group, only the generator itself and its inverse can reach every power that is positive and negative necessary to cover the group. That's what we proved. we took two cases. We took the case of plus and minus 1, and then we took the case of k greater than 1. And we proved that plus and minus 1 gave us all the values of the group, but in case of k greater than 1, we did not get all the values. Either we get the odd values or we get the even values, right? Therefore, we cannot cover the entire group in that case. So the only generators could be a and a minus 1, a raised to minus 1. All right. So that's all for this video. Here we made sure we could understand the two types of generators, that is for a finite group, a cyclic group, and an infinite cyclic group. So just to revise, for a finite cyclic group, the generator is a raised to k, and we use a formula which is order of ak to find the to prove this thing, right? And for an infinite cyclic group, the generators are a raised to 1 and a raised to minus 1. All right, we took two cases. The first case where a is equal to plus or minus, where k is equal to plus or minus 1, and the second case either k is greater than 1, so it could be 2, 3, or anything, right? And we proved that the generators could be only a and a raised to minus 1. That is, the generator itself and its inverse can only give us all the elements of the group, whether they are positive or negative. All right, so I hope it was made clear. Make sure you try to understand the theorem first whenever it comes to you in the exam, understand what is being asked, and then move forward to the proof, so that in that way it will be easier for you to keep the question in your mind and then understand what you're trying to prove, and that's going to help you in each and every step. All right, so that's all for this video. Make sure you like, share, and subscribe to my channel. If you have any questions or any theorem that you want me to solve, I'm here to help you. Make sure you write it down in the comment section below. Also check out the previous videos in the group theory section, as well as in the applied mathematics portion as well, which I have also started. Also, there are general knowledge videos on my website, on my YouTube channel, so make sure you check those out as well. Everything is CSS related or any competitive exam related, so make sure you ask questions if you want me to explain something to you. I hope it was all clear. That's all for today. Thank you. Bye bye.